Hello everyone, and welcome to this next video lecture. So today we're going to talk about something called the Central Limit Theorem, and I want to warn us a little bit. This is the most theoretical thing you ever cover in an introductory statistics class, and it's important to cover because it's likely the most used result in not only statistics but maybe even all of applied mathematics. So it's certainly something that you need to know to be statistically literate. But that being said, this is a theorem. This is very much straight theory, which a lot of people find very difficult. So I'm going to talk about the central limit theorem. I'm going to try to motivate it and explain it to you. But ultimately, there are just two little things you need to remember about it. And if those are the only two little things you remember, then I will be happy as your statistics teacher at the end of the semester. So let's, without further ado or warning, let me dive in. So the central limit theorem. Something kind of fun. Before I do the fun thing, let me do an informal definition. The sampling distribution of x bar is approximately normal. So remember, hopefully in this most recent lecture before this, we talked about what the sampling distribution of x bar is. It is every single time I take a sample, I would expect to get a different x bar. So if I got a lot of different x bars and looked at how they were distributed, we would call that the sampling distribution. And something that is really quite marvelous and a very interesting mathematical fact is that those x bars that you draw from whatever distribution you're interested in, they will be approximately normal. And one second, maybe the examples I give will give more of a intuition as to why that is truly extraordinary. So let me finish this definition. This is a poor approximation when the sample size is small but improves for larger samples. And I have a quote, actually. This is the fun thing I thought I would share with all of you. There's this guy, his name is Sir Francis Galton, and you may have actually heard his name before from Galton boards. Have you ever seen them? They're like, you see a bunch of pegs and you drop a bunch of balls in the pegs and they kind of all fall down and they make kind of a distribution at the bottom. You should look it up if you've never heard of a Galton board, but that's where we get that name. And he he is quite the dramatic individual because he has this like paragraph he wrote about the central limit theorem where he calls it like the the law that rules the angry mob, and he says this one thing that I really like. I'm going to share with you. It is the supreme law of unreason. So that was Sir Francis Galton. The 1800s. So what is the central limit theorem? What does it mean to say that the sampling distribution will be approximately normal? Well, consider this photo. These are population distributions for X. So the idea is that we have a data set, and we're looking at three different types of data sets: the uniform, which we know very well; one we haven't touched upon, but it's just another different type of density curve called the exponential; and another one we haven't really touched upon, but again, it's just a different type of density curve, just like the normal and the uniform and the triangle. It's called log normal. So the idea is these are the distributions of our X values that we've observed. Our data is distributed uniform, distributed exponential, distributed log normal. And what we've done is we've taken the sampling distribution of X bar for when n is equal to 2. So this is 1 over 2. If we took a sample of size 2 and calculated X bar, and then we calculated a ton of X bars and looked at the distribution of the X bars for a sample size of 2, they would follow approximately these distributions, right? So a little bit different because this is like a calculation of our data, but the blue here, the light blue, shows us what our sampling distribution is. And the dotted lines show us what a normal distribution would be if it had the same mean and standard deviation as these sampling distributions. And what you should notice is as our, so this is xi from I equals 1 to 2. So these are a bunch of these. This is 1 over 5 if I took a sample of size 5 and calculated a bunch of X bars, right? Then the distribution of X bars would be these. This is if I took samples of size 12, and every single time I took a sample of size 12, I calculate X bar, and it would look like each of these. Now, what you're meant to notice by this photo is that the light blue is the distribution of the X bars, and as we increase our sample size from 2 to 5 to 12 to 30, notice how the blue line starts to look more and more like the dotted line. The distribution of the X bars is becoming more and more normal, which is exactly what the central limit theorem is saying. It's saying if you take a sample, calculate X bar, take another sample, calculate another X bar, and keep doing that and get a ton of X bars like we went over in the last lecture, then the distribution of them, if I were to make a histogram of all of those X bars and approximate my histogram with a density curve, that curve will be a normal distribution. And it doesn't matter what your original data was. And that is such, it is so hard to communicate how amazing that is to people who are just starting out in statistics. What's so spectacular about it is it doesn't matter what the original data set that I had was. If I had a uniform data set, I do this calculation, I do a bunch of X bar calculations, and all of a sudden I have a normal distribution, right? It's how did I go from a uniform to a normal? It's ridiculous, and it doesn't actually matter if it were a uniform or an exponential or a log normal. It works every single time. I do have a little bit of a caveat. So, but maybe I'll do it after this point. So the big idea is that the larger sample size we take, the more normal the sampling distribution becomes. So I hope this picture is somehow illuminating to it. If you don't quite understand, the thing that you should understand from this lecture is the following. We are going to be using the central limit theorem to do inference in our next lecture. And to be able to use it, we have to check certain conditions. And those conditions are the following. The sample we take must be a simple random sample, right? We have to choose our values independently and randomly. So each draw from your sample should be independent and from the same population. So we need a simple random sample is the first thing, because that simple random sample actually gives us independence. And two, your sample must be large enough for the approximation to be meaningful. And what this gets at is, note when n equals equal to 2, the sampling distributions didn't look all that much like the dotted line, right? This one is not normal. It's still kind of skewed to the right. Whereas as our sample size, as the amount of data points we put in to calculate an X bar increased, these distributions became more and more bell-shaped. They became more and more, the blue line became a lot more like the dotted orange line. And that's what this next thing is saying, is that if your sample size is really, really small, the central limit theorem isn't actually going to help you all that much. You need larger sample size. And the ad hoc, and I say this with a bit of reservations, is the ad hoc value is to have a sample size greater than or equal to 30. But this can truly vary on the situation. Depending on the situation. I'm also going to add in the distribution should not be strongly skewed. Since this will reduce the accuracy of our approximation. So that kind of gets at, note that the log normal is very strongly rightly skewed, and even when we had n equals 30, it's kind of outside. If you look at the top, it's kind of outside of what it should be if it were normal. So skewness definitely comes into, if you have a large enough sample size, it can sometimes wash out the skewness, but it's something that you should definitely look for before you decide to apply the central limit theorem. So let's do an example. Maybe that'll help us understand how it works. Say we took a simple random sample of size 40 of squirrels. And measured their tails, the girth of their tails. Suppose squirrel tail girth is distributed uniformly between 5 centimeters and 25 centimeters. So remember we talked about uniform distribution. Every single value in between 5 and 25 is sort of equally likely. And my question to you is, what is the probability of the sample mean being less than or equal to 10? So notice this is not asking what is the probability that x is less than or equal to 10, right? The probability that x is less than or equal to 10 is just, I would take the uniform distribution between 5 and 25. I would look at 10 and I would calculate the area under the curve here if I wanted that value, right? But that is not what we want here. What we want to know is something about not x, but x bar. We want to know how often over the long term will the value x bar be less than or equal to 10. Let me say it again. What is the probability that if we were to take a sample of 40 from this population, use that sample of 40 to calculate this value x bar, what is the probability that x bar will be less than or equal to 10, which is a very different question. We're not talking about the uniform distribution anymore, even though the data is from the uniform distribution. We're talking about like a like function of the uniform distribution, which is really kind of, it's weird. It's a new idea. But the answer is, by the central limit theorem, x bar follows a normal distribution with mean mu of x bar and standard deviation sigma of x bar. So I think we talked about what mu of x bar and sigma of x bar are. Expectation of x bar is equal to mu, right? So mu of x, here, I'll do it this way. The mean of x bar is equal just to the expectation of x bar, which I think we showed in last class that is just equal to mu in this case. And mu, let me do it a different way. Mu of x bar is equal to e of x bar, which is equal to mu, which in the case of the uniform distribution is a plus b over 2. It's something that we learned, which is equal to 30 over 2, or 15 centimeters. Okay? The standard deviation of x bar is equal to standard deviation of x, which, as we showed in class, is just equal to square root of sigma squared over n, which in the case of the uniform, sigma squared is equal to b minus a, so 25 minus 5, squared over 12, divided by our sample size here, which is 40, which is going to be equal to 0.91287 centimeters. Okay, so we have our mean, we have our standard deviation. Thus, x bar here is distributed normal with mean 15 centimeters and standard deviation 0.91287 centimeters. Thus, the probability that x bar is, what did I ask, less than or equal to 10? Right? Yeah, we want to know less than or equal to 10. It's just going to be an area under the curve calculation of a normal distribution that is centered at 15 Looks like I want to know less than or equal to 10, which is down here, which is going to be that probability right there, right? Cool. Well, let's give it a shot. So, oh, something to note, this picture isn't quite to scale. Since the standard deviation is so small, 10 is actually going to be way down here. So it's going to be like that. Sorry, my bad. So we do what we always do. Let's calculate a z-score. So what we want, 10 minus 15 over standard deviation, 0.91287, which is equal to negative 5.477. So we plug this into norm.s.dist. And it's going to equal 2.162 times 10 to the negative 8th, which is actually approximately 0. It's a very unlikely thing to observe. Okay? So that is what the central limit theorem allows us to do. It allows us to come up for a distribution for x bar. And x bar, as we discovered as a consequence of the central limit theorem, it doesn't actually matter what the distribution of x is. Well, it matters a little bit, but it needs to be independent, it needs to be not strongly skewed, but as long as it isn't either of these things, the distribution of x could be anything. Here it was normal, could be triangular, could be something else, right? The thing is though, if you're talking about the sample mean, x bar, that is going to be normally distributed no matter what the distribution of x was, which again, I cannot stress how big of a result, how big of a deal that is. And I hope if you all end up doing more statistics, you will come to appreciate it more and more. So I think I have a side note, and then that's it for this lecture video. You need not apply the central limit theorem. CLT is what shorthand for it. When the underlying distribution is normal or nearly normal. X bar is normal in this case, automatically. So if your underlying data are normal, you don't actually need to use the central limit theorem. You can just assume that x bar is normal as well. I know it's a bit of a nuance, but if I ever ask, are you applying the central limit theorem here? This is something you should check for. Like, do I really need to say by the central limit theorem, or can I just say, oh, x bar is normal? So I'll give an example of this. Using the same sample, of 40 squirrels, we'll now measure the lengths of their tails. It is known that squirrel tail length are distributed normally with this distribution, 15 and 5. What is the probability that x bar is less than or equal to 13 centimeters? So first thing you would do is say that x bar is normally distributed. But not as a consequence of the central limit theorem. Because the population from which we sampled is normal. So we now need the mean and standard deviation of x bar. So mean of x bar is just equal to the expected value of x bar, which is actually just equal to the expected value of x. It's equal to mu. In this case is 15 centimeters. Standard deviation of x bar is equal to the population standard deviation divided by root n, which in this case is 5 centimeters divided by root 40, or 0.79057. Is that correct? Yeah. So if we want to know the probability that x bar is less than or equal to 13, well, we just made the conclusion that x bar is normally distributed, right? With a centered at 15 centimeters. And we want to know the probability of being at or below 13. So that is this area right here. So what we do is we calculate our z-score. Which is going to be equal to negative 2.5298. And we plug it in to our norm.s.dist inverse, norm.s.dist. Which is going to be equal to approximately 0.00571. So the probability of us taking a sample of size 40 from this normally distributed random variable, calculating the value x bar, the probability that that calculation, that x bar, is less than or equal to 13 is approximately 0.00571. Okay? So this is the central limit theorem. If you don't fully understand the nuance of what the theorem statement is saying, what you should know is that it allows us to say that x bar is normally distributed, and allows us to do that sort of z-score calculation and probability calculation that we've been doing a lot already, as long as you have these three things. So if there are things to remember from this lecture, it would be these three things, and being able to say, x bar is normal by the central limit theorem, and I checked these three things. Okay? Hopefully we'll get a lot more practice with this in the future. Thanks, everyone.